Now we're going to have a look at question 2 from the team selection test. And what this question basically asked us to do was to consider a sequence of real numbers. So it was xn, where we initially had that x0 is 1, 0, sorry, x1 is 1, and then finally that xn plus 2. So adding on two indices is the same as 3 times xn plus 1 minus 2xn. And then the next question said we also have yn, which is equal to xn squared plus 2 to the power of n plus 2. And we need to show that yn is the square of an odd integer. So there are a few different steps to this. We first kind of want to find a way of expressing xn somehow. And then from there, we want to find what yn is. And then we want to show it's something squared, right? Something here, and the thing that it's a square of, we want to show that it's odd. So let's try and do this. So we know that here that we have a linear recurrence. Okay, so whenever you have a linear recurrence, you know that the solution is always xn equals alpha to the n of some form, right? Of alpha to the n. So what you can do now here is go that alpha to the n plus 2 equals 3 alpha to the n plus 1 minus 2 alpha to the n. And we cancel all the ends, and we basically get that alpha squared equals 3 alpha minus 2. Now we can write this as a quadratic equation as basically alpha squared minus 3 alpha plus 2 equals 0. And this means that alpha minus 2 and alpha minus 1 equals 0. So alpha equals 2 or alpha equals 1. In fact, what this means is that xn equals a, some constant a, times 2 to the n plus b times 1 to the n. And what we can then do is realize that that means that xn just equals a times 2 to the n plus a b. And we can use our x naught equals 0 and x1 equals 1 to solve this. So we know that 0 equals a, and 2 to the power of 0 is just 1, plus b, and 1 equals, well, 2 to the power of 1 is just 2, so 2a plus b. So you're solving simultaneous equations, well, you can just subtract the first equation from both sides, so then you can just get 1 equals a and minus 1 equals b. So what we essentially get then is that xn is just 2 to the power of n minus 1. And you can plug in some values of x and of x0, x1, x2, x3, and you'll find that this thing works. Another way you could have done it is just by plugging it in and then guessing this pattern and proving it using induction. Proof by induction. And in fact, I would often go ahead and still prove this with induction. I mean, the method that we use with finding this characteristic polynomial is fine and will work for all recurrent series, but it's better to just prove it by induction so you can be sure that the value is 2 to the n minus 1. Okay, so now let's clear this stuff up and continue. So now that we have this particular thing here, what we know is that xn, as I said, let's keep it here, xn equals 2 to the power of n minus 1, and yn equals, what was it? It was xn squared plus 2 to the n plus 2. Let's plug this in. So this is 2 to the power of n minus 1 squared plus 2 to the power of n plus 2. This we then expand as just 2 to the power of n all squared minus 2 times 2 to the power of n plus 1 plus 2 to the power of n plus 2. This is just the same as 2 to the power of 2n minus 2 to the power of n plus 1 plus 1 plus 2 to the power of n plus 2. Now this still looks strange. It's not exactly a square yet, but we notice that this is a 2n, and that's kind of 2 to the power of n all squared. This is an n plus 1. This is an n plus 2. These are kind of related, like 2 to the n plus 2 is just the same as 2 times 2 to the n plus 1. If we write that out, we get that this is just 2 to the 2n plus 1. I'm going to keep that there. Then minus 2 to the n plus 1 plus 2 to the n plus 1 times 2. Then this is kind of like minus a 2x, right? Plus, sorry, minus an x plus 2x. So that's just, we can simplify this as 2 to 2n plus just an x. So plus 2 to the n plus 1 plus 1. Now this is actually just 2 to the 2n plus 2 times 2 to the n plus 1, which is just 2 to the n plus 1 all squared. Now this number in the middle is an odd number because this here is even, and this bit 1 makes it an odd number, and then this, it's a square. So this is an odd square. An odd square, which is exactly what we wanted to show. So that's what it was. It was linearly recurrent series that you should review, and then just playing around a little bit with exponents and plugging things in and squaring things and messing around with them. But yeah, that's the question. Let me know if you have any questions. Thank you.